Hi, everyone. This is the second lecture on dimension reduction. And so I'll start by quickly saying a few words about PCA before moving in to some other methods for dimension reduction. Okay, so last time we had this graph, and if you recall, this is a biplot. It's showing information about our lower dimensional embedding using PCA. And I received some questions about how we know that furniture, floor, and animal influence the second principal component, for example. And the reason is because these are nearly parallel to the second principal component, which is over here on the vertical axis. And likewise, things like bathroom and number of parking spaces, those were nearly parallel to the first principal component. Okay. Another just quick question here. So the principal components are uncorrelated, and I wanted to just briefly say a word about that. So on this slide, I have just some math that you can use to see why this is the case. In the central idea is that the eigenvectors are said to be orthogonal, which means they're at right angles with one another. So this makes a lot of sense in 2 or 3 dimensions for us, right? So we can in the Cartesian plane, we know that the vertical axis and the horizontal axis are at 90 degrees, right? And that these 2 vectors, they're said to span R2, the entire Cartesian plane. You can make any vector using these 2 as a basis. In 3 dimensions, in X, Y, Z, those axes are all at 90 degrees from one another. So there's a nice geometric intuition about that. So when we do an eigendecomposition, the eigenvectors are also orthogonal, and they span a space of dimension equal to the rank of our original matrix. It'll mean, because our principal components, remember, we're multiplying our original data by our eigenvectors, well, then they'll also be orthogonal to one another. And this orthogonality, it means the same thing as non-correlated or uncorrelated. So yeah, and if you're curious on more of this, I encourage you guys to look at some of the materials that I put online. And there are also many mathematical texts that go through the proof of principal components. And if you guys are interested, ping me, and I'd be happy to send you some other sources for that. Okay, so without further ado, let's move on to some other dimension reduction techniques. And we're going from the classical to the modern. So aside from PCA, there's a very common method used to reduce dimension called multidimensional scaling. And multidimensional scaling it's different than PCA in the sense that now we're using a proximity matrix rather than a covariance or a correlation matrix. So the covariance or correlation matrix in PCA has dimension equal to the number of columns by the number of columns. In MDS, we're computing a proximity matrix. And so if we have n rows and k columns, the proximity matrix in MDS can be n by n, right? It's telling us how similar the different rows are in our data, versus in PCA, when we compute a covariance or a correlation, we're seeing how similar the variables are. So what's the big idea about MDS? Well, in MDS, we're interested in preserving the distance between points. So we know the distance, in the higher dimensional space, right? And then we'd like to preserve these distances when we choose a lower dimensional representation for our data. All right, so here's kind of the big idea laid out. All right, so let's let the matrix D here be an n by n matrix. And so it's giving us pairwise distances between the rows. So, row 1 and 2, 3 and 4, so on and so forth. So then what we want to do is we want to choose a low dimensional embedding of data points, say with L dimensions, right? We're typically going to choose L to be 2 because then it's very easy to visualize that. So what we want our distances in the lower dimensional representation to be approximately equal to the distances in the higher dimensions, right? And so we have an objective function that we can minimize, and that's called the stress. So kind of fitting for the time in which we're all living now, right? And so here's the stress function. So this is the distance between I and j in the lower dimension, and then here are the original distances. And so you see this is kind of like a sum of squares, right? It looks a lot like the sum of squared residuals that we minimize for OLS. So just something to keep in mind in terms of robustness later on. So you can use the Euclidean distance here. You can use other distances as well. And so in that way, there's a little room for creativity with MDS. Okay. All right. So here's a quick example of how MDS works. So let's plot some points in 2 dimensions. And some data I have here, and this will be up on Canvas. It's measurements of opossums taken from 7 different locations. I'll call them burrows. I don't know if that's an actual name. If you guys know, let me know. Probably could just look it up, but I won't. All right, so I'm going to fit a low dimensional embedding using the measurement columns, and that's what I've done. And so this plot shows the two dimensions, the lower dimensions, and those points, that's the lower dimensional embedding, and then I've colored them according to the site or the burrow to which the opossum belongs. So it's kind of interesting, and one thing you can see here is that the MDS actually does a pretty good job recovering the burrow structure. So you see, it seems like sites 1 and 2, they're pretty similar to one another, but they're clearly separated from the other burrows. And so you might be asking yourself, well, how is this working? I mean, what's going on here? How could this be? Keep in mind, I did not include any information about the site or the burrow to which the opossums belong. So this is all being inferred from the measurements. And so the idea is that within burrows, the opossums have similar measurements, right? So these are the families, right, or the larger families. And so then they share some, say, genetic information, and they tend to have similar measurements, and that's what this is picking out. And so by looking at something like this, you might infer something about the animal dynamics, how these animals are related. Perhaps at the different sites they have some shared ancestors, especially between 1 and 2. It looks like it's quite likely. Okay, so here's how I did this. So I loaded possum data. There are 2 data sets. One has the measurements. The other has the burrow locations in longitude and latitude. So I didn't use that in this analysis, but feel free to play around with that. So it's pretty interesting data. And here I've used the CMD scale function to do MDS. This is a very basic function in R, base R. And so I've chosen k equals 2. That's the dimensions. And you see I've used this function d equal dist as matrix, and then my possum matrix inside there. So what I've done is I've computed a distance matrix between all the points, and that's what's inside there. So now I'm making the plot. So this simple stuff. So I'm naming the columns of the results I get out of my call to CMD scale. Then I'm using ggplot in order to create the scatter plot. All right, so we've taken data in 7 dimensions, a bunch of measurements, right? And we've been able to embed them in 2 dimensions, and it's giving us a pretty clear idea about the relationship between these different groups of opossums. Okay, so we have some diagnostics to understand how well this is all working. So we said that the function we're trying to minimize is called the stress. So we choose these points, or locations in the lower dimensional space to minimize the stress. And so if we choose 2 dimensions, we will do the worst, right? But then as we add more dimensions, we'll be able to lower the stress. And so this shows what I've done is I fit the stress for different Ks, or in this case Ls. We called that L earlier. That's the number of dimensions in the reduced space. Okay. And we see that the stress when I had 2 dimensions is about 0.14, so 14%, and it drops off pretty quickly. We had so you can see this is similar to the graphs we looked at regarding PCA and the percentage of variation explained by the different principal components. As we add more principal components, we're able to explain more of the variation. And so what this is basically saying is that as we increase the number of dimensions, we're able to approximate those distances better and better. All right. So there's some heuristic, rules of thumb regarding what you want your stress to be. And so you see 10% and all this other stuff. So I wouldn't take that, take it all with a grain of salt, right? It's ultimately it's about what you're trying to discover with the data and what you're trying to do. So here, a 3-dimensional representation might make sense because we see that stress drops quite a bit. We know with 4-dimensional, that's not really that helpful for us. We have a hard time visualizing that. Okay. Let's see. All right. So we're able to also create a jackknife. Let's see. The color of my presentation was just changed. Okay. Anyway, we'll work through it. Okay. So I have some data on countries and their energy use and how much CO2 they emit into the environment. And we ran MDS on this data set, and then the SMA COF package, which we'll learn more about, allows you to perform a jackknife. So we're dropping, a country from the data, and then running MDS. So computing the 2 reduced dimensions, and then saving the results. And so this plot shows in 2 dimensions some of the richer countries in the world. One thing you note is that the United States is up at the top, and so it looks like a bit of an outlier. That shouldn't be much of a surprise. So the United States is a big polluter and uses a lot of energy. And you see Australia is nearby, and then down on the other side, you got Norway, Luxembourg, Kuwait, Oman. All right, so I'll just say a brief word about all these lines that we're looking at. So the lines indicate how the fit has changed across all of the jackknife replications. So we have, I don't know, maybe 30 or so countries here, and that's showing you that as we drop the points, how the projection for that country is changed. And then in the middle, that's the average of all of them. And so you can get an idea for the stability of this projection into the 2-dimensional space for each of the countries. So the United States is pretty stable, and that really speaks to the fact that it's an outlier and it really controls the fit of MDS. whereas some of these other countries, they move a lot around quite a bit, right? As we drop points. Okay, and so here's some code how I made that plot, and then it's reproduced over here. So there's this data called electricity CO2 clean. I'm dropping one of the columns here, and I'm keeping all the countries that have a per capita GDP of 15,000 or more. And so now I'm running MDS with this different package here. It's SMACOF. It's a wonderful package. I highly recommend it. So I'm scaling the data. So why am I scaling it? Well, if you take a look at it, you'll see that the columns are very different. They don't have the same units of measurement. And we know that you might be worried about biasing your results if there's a lot more variation in certain dimensions than others. So now here, I am creating my distance matrix, loading the package, fitting. So this is going to do metric MDS, this function here. And now finally, here's the jackknife, and it'll do the jackknife for you. You can plot it, and you'll get nice plots. It's very nice. Okay, so we can also do this for the columns in our data, not just the rows. And so here's an example. We have a data set on diabetes, and so there are several different biological markers that were taken, and then we also have a column indicating whether or not an individual has diabetes. And so for this, I didn't use the information about whether or not someone has diabetes. I just took all of these other pieces of information. And so what I've done here is now created a matrix of dissimilarities for the variables, right? Not the observations, so not the rows, but the columns here. And I've plotted them. And so how close they are to one another gives us an idea of how related these different variables are. So we see that age and pregnancies are pretty close to one another. And that reflects, the fact that, so this is a data set of women, that you're, more likely to have a larger number of pregnancies the older you are, which, that makes a lot of common sense. We see that these are pretty noisy because we jackknife them, and you can see how they move around as we drop the different columns here. Whereas insulin's not, right? Insulin is pretty robust, and that's an indication that insulin is probably pretty important here. Same thing with skin thickness and BMI. Okay. So then here's some code how I did that. So this is a variable distance. I found the correlation between the different variables here. And what I've used is function sim to dis. And so so correlation is a measure of similarity. And this function takes and measures dissimilarity. So this function will convert that to dissimilarity. And you can go ahead and read about the ways that they do that in the documentation. And we're fitting it. And I've shown some code here how you can actually do a bootstrap. So I recommend you try this out. It's kind of cool. But what's plotted here is the jackknife. All right. So some weaknesses of MDS. So as I said, the stress function looks a little bit like a sum of squares. Because of that, it tends to privilege or to try to preserve large pairwise distances over smaller ones. And so, outlying points can have a pretty big effect on the fit. So again, this is similar to what we learned about with OLS, that points with a lot of influence really change the slope of the best fit line. So for example, this is just showing the distance matrix between all the countries in our CO2 data. And the brighter it is, the larger the distance. And so you can see the US is pretty far from almost all of these countries. And so for that reason, it has a lot of influence over this. We saw that in the fact that the United States moved very little on that jackknife plot. So this is something to keep in mind, and it's a weakness of this method, to be sure. There you go. All right, so MDS is not it's not the only thing that we can do aside from PCA. So there are many modern methods, and I'm going to introduce you to two of those. So first, Isomap. Um, so Isomap, it has some similarities to MDS, and then some important differences. So we'll talk through that. So with Isomap, we begin by creating a neighborhood graph. So we look at all of our points, and we find the k nearest neighbors for each point. And then these points are connected in a graph, and they're assigned weights, according to those distances from their k nearest neighbors. So then this gives us an idea of the connectivity between points, or which point is a neighbor to others. And then from this, we compute the geodesic distances between all pairs of points in the graph. So this becomes a distance matrix, right? Similar to the ones that we use in MDS. So then the third step, we actually apply MDS to this shortest path distance matrix. So Isomap includes MDS, and this is an example of how MDS can be very useful and used inside other methods. So just to elaborate a little bit more, so step one is preserving what we call local features of the data. So making sure that we have the same neighbors in the higher dimensional and lower dimensional spaces. And then 2 and 3 are going to create some global structure. All right, so this is best seen with an example. So here again is our possum data. And what I've done is I've run Isomap here, and we're looking at the network plot associated with the data. And I think I chose k equal to 5 nearest neighbors here. And so you can see for each data point, it is linked to its 5 nearest neighbors. All right, now here I've overlaid the borough information. And so you can see that similar to MDS, we have some good results in the sense that we're able to pull apart boroughs 1 and 2. Those are the red and orangish ones from the others. This doesn't look exactly like what we got from MDS, and we shouldn't expect that it will, because this is a different method. Whereas in MDS we're using the Euclidean distances between all points, here we're using Euclidean distance for the k nearest neighbors, and then we're finding these geodesic distances. And so to get an idea of what that means, so let's find the geodesic between this point and this point, for example. It's this, doot, doot, right? And so it's this distance here, right, plus this distance here. So so it's a different notion of distance, and therefore we're going to get different results. So it's a nice picture, and we get some interesting structure emerges from it. So here's some code that shows how I perform this. So first, you can find, there are a few different implementations of Isomap in R. And the one I've used here is in the vegan package. So I recommend using that, but feel free to explore other implementations. So here I've run it on the possum data. I've chosen to embed it in 2 dimensions, and I chose my number of neighbors to be 5. Net equals true means that when I plot it, I want to see the network. I think the network plots are pretty interesting, as it gives you an idea of how this was actually done. So now down here I plot the results. Here I'm using Rainbow HCL to choose colors. And again, I've colored them by the site. And I put my legend down here. Okay. Now I'm going to do this with the diabetes data now. So I used our diabetes data set, ran Isomap. Now here I've chosen 10 nearest neighbors because there are far more rows, over 500 of them in this data set. And now you can see that it seems to do okay in terms of separating these 2 groups. Not perfect, right? But what we do see is there seems to be one large component, right? So this means this is a group of people who all, they share similar features. And then there's this group of outliers down here, right? So if we were to analyze this data, we might break this into parts. So that is to say, you might want to have, if you're trying to predict whether or not someone has diabetes, you might build a model for this region, and then you might build a model for this region. Some of these other points may be outliers, right? So it may not be easy to predict whether or not they have diabetes, because they may be atypical cases. Okay. So finally today, let's look at one more method for dimension reduction. It's the stochastic neighbor embedding. So this is an even newer method, and so let's compare it to Isomap and kind of see how it works. So Isomap makes use of local neighborhoods to estimate a lower dimensional embedding. Here we're doing something similar, but now what we're doing is we're computing a probability that point J is going to be a neighbor of point I in the higher dimensional space, and we would like to find data points that will make those probabilities, the PJIs you're looking at there, similar to these QJIs in the second equation. So if it's a neighbor in the higher dimensional space, we want it to also be a neighbor in the lower dimensional space with high probability, right? I've posted a paper on Canvas that explains all the details here. So the idea, and I'll just read this, this here. The similarity of data point xj to xi is a conditional probability, pj given I, that I would pick j as its neighbor if it were picked in proportion to the normal probability density centered at xi. So you can imagine centering a normal distribution around xi, and then asking yourself, well, what's the probability if we were going to just select one point around xi? What's the probability that we would pick xj? And that's the idea of this probability. Same idea going on down here. Okay. So then a few years later, this method was updated, and the probabilities are symmetrized in this way, and the definition of the QIJ was also changed. So this is simplified and found to improve the results quite a bit. And so then points are chosen to minimize this objective function. And so for those of you familiar with the KL divergence, that's what this is. And so the idea is you're choosing these things, to minimize this, right? And so the idea is these QIJs can be written in terms of the Z's. And so the lower dimensional projection minimizes this objective function. All right, so let's look at some examples of this. So here's the diabetes data set again. And with a perplexity of 100, I'll explain what that is in just a second. So we see that it does an okay job separating the points. We see again this idea of a main component and then a smaller component, like we saw with Isomap. No, it's not perfect, right? The separation is not perfect, and that's not necessarily a flaw of the method. That's just how the data generating process works. Now, I chose this measure called perplexity equal to b100. And so if we go back a few slides, you'll see that in here we have this the sigma term, okay? And so that sigma term ends up being used here as well. So we need to choose a variance for the normal distributions around our points. So that is to say, how far do they extend, right? How quickly does the density decay around that point? So this is a parameter that we choose, and we don't choose it directly. We actually choose what's called the perplexity. And so the idea is that as the perplexity is increasing, then we're increasing our variance, right? We're increasing the density around these points and making it more and more likely for points farther away to be picked as a neighbor. Okay, so it's very similar to increasing K in Isomap. That's kind of some of the intuition there. So changing the value of the perplexity will definitely change the local geometry and therefore the global geometry of the embedding. And if you're interested in what the perplexity actually is, it's equal to it's 2 to the Shannon entropy, and the Shannon entropy is defined down here. So it's not essential that you understand all of that. What is good to know is that, so we have these PJIs in here, and remember the PJIs are functions of the sigmas, and so that's how they're all related. But if you understand that the perplexity, that increasing the perplexity is similar to increasing K in Isomap, then this will make some sense. Okay, so here's how I have run this. I use the our t-SNE package. And so similarly, it takes distances. And so I scaled the diabetes data here, chose my dimensions be equal to 2, have a perplexity equal to 100, and theta equal to 0. So this is telling it to use the exact solutions and not to approximate. That has to do with how it's computed. I think you could the default is 0.5. It runs faster if you use an approximation here. We're not concerned about time. So you can use theta equal to 0 unless it's really time sensitive. And now I've plotted the results down here. So I've extracted my my lower dimensional representation, labeled the various parts of my my graph, and included my legend. Okay, so I also ran this on the opossum data. And what I did is I varied the perplexity in the different plots because I wanted to give you a feel for what this is doing. So what we see up here, this is low perplexity equal to 1. It creates many small clusters, right? And then as I increase it, the number of the clusters begin to merge, right? So again, if we're using this idea that the perplexity is similar to the number of neighbors, you can see there are very few neighbors here, local neighbors, and now the number of neighbors increases, right, until we have what looks like two large components down here. So what's the right answer? Well, that's really going to depend data set to data set. There really isn't a right answer because we're doing something called unsupervised learning here in terms of learning the clusters or the shape of the data in lower dimensions. What we do see though is we do see that it becomes pretty stable. So these, so here we have this component, this component, this component, this component, right? And they're just kind of turned on it's turned on its side a little bit. But these actually look pretty similar between 25 and 30. These are pretty similar as well. I would argue that, I would argue that it starts to look pretty similar at 8 and beyond, right? And so you might pick one of these values here between, maybe 20 would be a good one to pick, 25 could be a good one to pick here. So it's a good idea to try different values of perplexity and see the results. If you see that for, that a certain result or feature or grouping is present from all the different levels of perplexity you try, then it's a pretty robust result. So one thing to mention is this algorithm was developed for visualization. And so, it's tempting to want to do data analysis on the lower dimensional representation of our data. And there are methods to do that. There are regression methods, for example, associated with PCA. For this particular method, stochastic neighbor embedding, it's not really clear how that works. And so just a little bit of warning that this is primarily for visualization. Also, how we use perplexity and a way to perhaps optimally choose it is still an area of research. So if that's interesting to some of you, you can probe around. Yeah. So anyhow, that's t-SNE. All right. So this concludes the second part of our lectures on dimension reduction. You'll be able to work through some of these issues in the optional lab that I've posted. And yeah, thank you for your attention. And take care of yourselves.